Okay. Hi. Hello, everyone. Hopefully you can hear me. So, welcome to the Data Structures Exam 1 review, where I'm your TA, if you don't know me already. And so, let's get this started. So, we're going to cover four main topics. So, the main one's going to be Big O, time complexity, recursion, and linked list. And we're going to take it one by one. So, we're going to take it slow. And so, let's go straight into the knowledge. So our best time complexity we're ever going to see is going to be O of 1, where a function, algorithm, anything will basically complete instantaneously. So for example, inside a linked list, if I want to delete from head, and since head is could be the first node for every single instance, we can it will delete the head at O of 1 time, very instantaneously. And the next best thing, this could be O of log n, where this will be very common whenever we use like binary searches, any any point in time where we divide the input size by 2, and so on and so forth. And another one that's pretty average, that's in the yellow, is could be O of n. And you're going to see this a lot in this course. So whenever you're sorting and we're using a basic sorting algorithm, like the sort inside the algorithm library in C for C++. And if whenever you use a for loop and you're not modifying the input size, it's a pretty common time complexity, which is okay. And when we get to the red, those are like one of the worst time complexities ever. And we usually try not to aim for these, but it does happen, and that's okay. So like some more common ones we will see in this review is going to be O of 2 to the power of n. Very common with recursion algorithms, but we'll get there when we get there. And so let's move on to a time complexity. And so in a very quick summary, time complexity is the measurement of how long an algorithm runs based on input size. That's it. And we use Big O Notion to determine, wait, what is the time complexity for this algorithm? Straightforward, hopefully. And so let's look at this quick example based on this function down here. So we have input size of n, and we can see we have a loop that will iterate between, that will have int I go from 0 all the way until we reach n. And so right now you're like, what is this guy's talking about? What do you mean that we only have like three simple conditions? And that's okay. So for time complexity, really important note to take away is that we need to worry about two things. First thing is going to be input size. And in our case, input size is going to be n. And the second thing we need to worry about is how long are we using this input size? So through a loop, recursion, while loops. And so we're just wondering, hey, how long are we are we using n? Or n will be the input size. Really important. So going back to the problem, we see n is not being modified at all, which is great. However, we are using n all the way from 0, where we are at the starting point, all the way until we reach n. And so we can just say, using big O time complexity, we can just say, okay, our function is going all the way, it's going to have a time complexity of big O of n, where we just go from 0 to n. And don't worry if everybody's confused. We have multiple examples from here on out, but just to confirm that I'm not going crazy, it's gonna be O of n. Yay! So let's move on to another function. And so for this function, we can see we have input size of n not being modified, which is good. But this time we have two for loops. One that will start from 0 and will go all the way to 100. So let's keep a note of that real quick. So we go from 0, oops, wrong one, from 0 all the way until 100. Okay, and now let's check the next one. So we're going from j will start at 0 and we're going to go all the way to n. Okay, so we've seen this one before. We know that we're going to go start from 0 and go all the way to n. And we can assume, based on our previous example, that this inner for loop will have a time complexity of O of n. However, we do have a previous for loop. So for this case, we have to do a little bit something different. And so quick notes to have here is that whenever you have a nested for loop, always use multiplication. And so what I mean by that is that we're going to combine both for loops. Since the first one goes from 0 to 100, we can just say, okay, the outer loop will iterate 100 times, and our inner for loop will iterate n times. And for time complexity's sake, we can just drop the constant itself. So we can just say, okay, instead of being 100 times n, we can just say, oh, we're going to have a time complexity of big O of n again. And if we go to the next slide, we can confirm, yes, that's correct. Sweet. Hopefully you guys are getting the gist now. So let's keep going. So we have another time complexity again. And so let's keep track of two things this time. So we do have an input size of n, but we also have an input size of m as well. So we have to keep track of two different input sizes. That's okay. Nothing wrong with that. However, we do see that our starting point this time is going to be the input size itself for both for loops. And we do end at 0. So we're de-incrementing. And that's okay. It doesn't change anything at all. So we just say, okay, we're going to go from n to 0 and m to 0 as well. However, we do see one interesting change from the previous examples. We do see that our I is iterating by half. So we're not going all the way from 0, we're from n to 0, m to 0, like 1 by 1 by 1. Instead, we're going by halves. And so a little note to keep track of is that whenever we see half, we're most likely going to use log this time as the second best case from the big O chart. So little note, if we see half, assume we're going to use log with base 2. And so, okay, great. Let's use that. Let's use that little note we have. So we can say that our first for loop will iterate from n to 0, so it'll be n times, but since we're going half, it'll be log this time. So we can say log of base 2, where 2 will represent how much we're dividing our I, and we have our input size n. And from the previous example, we can tell, oh, we have an inner for loop, so we have to use multiplication again. So for the second for loop, again, we're going by half, so we can state we have log base 2, and our input size will be m. And this will be our time complexity. We have a time complexity of log to the base of 2n times log to the base of 2m. Or we can just drop the constant itself again as the other example, and we can just say, okay, we just have a time complexity of log n and another time complex and times log m. And that's our answer. That's it. Hopefully, y'all guys are keeping track. And so let's go through a more challenging example where we have, instead of a for loop that we got used to, we have a while loop this time. But that's okay. Nothing changes here. So let's keep track of our input sizes again. Okay, so we have n as our parameter. Sweet. We have I and j, where I will start at 0 and j will start at 1. Okay, pretty sweet. So let's read the first while loop. We can see that we go from we'll keep going until I is less than n, and we are iterating by 1. Okay, so it's pretty simple. It's like the other for loops we have encountered already. So we go from 0, then 1, then 2, all the way until we reach n. And then for our inner while loop, we can see we have the exact same condition. Okay, sweet. However, we're multiplying by 2 this time, which is very different from like going 1 by 1 by 1, where if we go 1 by 1 by 1, we should have a big O of n. So let's think back of how this is going to be counting. So we're going to start at 1. So we're going to have 1, then we're going to have 2, then 4, 6, 8, all the way until we reach n. As you can tell, the inner while loop is going a lot more faster compared to the outer loop. And for some reason, increasing it by 2. So if we look back to our original notes, we said that whenever we are de-incrementing our input size by 2, we're basically halving my big time complexity. So we can say, okay, so we are iterating a lot faster by 2. So theoretically, we can also say that, hey, this time complexity also has a log base 2 of n. And since these are two inner loops, we can use the exact same principle of multiplication. So we can say O of n times log base 2 n. Or we can just drop the constant itself and just state, okay, we have a time complexity of n log n. Dropping the constant. And that's correct. This is our final time complexity for this function, which is correct. Yay. So hopefully that was a good review on time complexity. So let's move on to some quick recursion real quick. So I'm not going to spend too long on this topic since it's pretty fresh still. So let's keep on the most important parts. So recursion has two specific parts to it, as a base case and a recursive call, where the recursive call will be the part where the function calls itself, the recursive part, and the base call will be the condition to stop, which is kind of nice. So we need to worry about the base case and the recursive call. That's it. And we can look at an example right here where we have a factorial recursive function, where our base case will be on the top, where we state that if ever n is either 0 or 1, we are going to return 1, as that's how factorials will work. And our recursive call will be at the next line, which is down here, the return, where you just say our recursive call will just be n times factorial n minus 1. And little keynote to have here is that whenever you do recursion, always include a return statement every single time. And so let's look at a really quick example of how we can use recursion. So given this LeetCode problem, that is a legitimate LeetCode problem, I swear, is that we have the power of 4. So we're given an integer n, and it returns true if it is a power of 4. Otherwise, return false. Pretty simple. And we can state that a n is a power of 4 if there exists an integer x such that n will equal to 4 to the power of x. Pretty simple. So for example, if we plug in 4 to the power of 0, we get 1. 4 to the power of 1 is 4. 4 to the power of 2 is 16. 4 to the power of 3 is 32. 4 to the power of 4 is 64, which should be down here. It's a little bit key visual for y'all guys. So we have to answer two things. What's the base case and what's the recursive call? So there's an instance where we can tell that, okay, can we figure out what is our base case first? So let's draw this out. So let's say I'm looking for 0. 0 is 0 every power of 4. The answer is no, it's not. How about 1? And as we checked earlier, it is. And now let's check again. How about 2? Wrong again. Yikes. How about 3? Oh, not the right number I'm looking for. So how about 4? Okay, 4 it is a power of 4 itself, which is sweet. Okay. So using a few C++ tricks, we know that there's a modulus function that exists already. So we can state, okay, what if we check if 4 is a power of 4? Let's do it manually. So we can say, okay, 4 mod 4, which should equal to 0, which is true because it is divisible by 0. But now let's do half. Well, let's divide this n by 4th instead. So this would say, okay, divisible by 4, sweet. Now let's check. 4 divided by 4 is equal to 1. Now the question is 1 the power of 4? It is. So we can state, okay, sweet. We have verified that 1 is also a power of 4 based on our previous list of powers of 4, and we can say, okay, it is a power of 4. So if these two conditions are true, it has to be true. And so let's check, let's say 8. So 8 is divisible by 4, which is true. So let's do 8 mod 4 should return a 0. But let's double check what if the other remaining numbers is also, if an integer x does exist, that it will be a power of 4, as the problem states. So let's do 8 divided by 4, which is 2. However, is it neither a 1 or a 0 from like our base case on top? So let's do mod real quick. Mod 4. However, it's not going to be 0 at all. It's going to be 8 or 2, I think. To be honest, I completely forgot. But we can state it's not going to be 0. Because that's true. 2 is not divisible by 4. So we can state, okay, 8 is not going to be the power of 4. So it is divisible by 2, but not, it is 8 is divisible by 4, but when we do a recursive call again, we can say 2 is not divisible by 4. So 8 will never be a power of 4. And so that's how our algorithm will work. We can say, okay, for our base case, if n is equal to 0, then return false. Because we know that's never going to happen. So how about 1? So if it is 1, then return true. Because technically, yes, the 1 is a power of 4 when we use 4 to the power of 0, which should be return 1. That's correct. But what's the recursive call going to be? So based on our simple example, we can state, okay, we can just say a recursive call can be n mod 4 and calling the function again by dividing by 4. So we can just say for now, since we don't have a function call, we can say function, and we're going to divide our n by 4. So we can double check this condition again. And the condition I'm talking about is this one. So let's go to the next slide and check how we're going to solve this, well, through code, which is correct. Yes, we do have a base case where if it's 0, return false. Else, if it's 1, return true. And we're going to do the recursive call again, where we do n mod 4 will it should equal 0. If it doesn't, we'll return false. And if it is 0, sweet, it's true. And we're going to check its other variables and check, hey, are these other numbers power of 4? It is. Cool. We know we got a power of 4. But question is, what's the time complexity for this function? Because it's a little bit more harder to read now, right? So, and that's okay. So let's break it down one by one. So we can tell that we have a n integer as n for input size, and we have two if statements here. And since we're just doing comparisons of returning false, we can just state, oh, okay, not to worry. We can just say this will take a time complexity of O of 1. This will also take a time complexity of O of 1, where we're just doing simple comparison and returning either true or false, ones or zeros. However, our recursive call this time is doing something else completely different. So here's another comparison. So we're going to say it's doing O of 1 again, but for the input size for the parameter, we're dividing it by 4. And based on some other examples, we also saw that we were dividing by 2, multiplying by 2. So we're reducing input size by 4 every single time. So we can state, oh, I've seen this before, based on a little note and line left behind. We can say we have a O of log 4, base 4 this time instead of 2, and we have n again. So our time complexity will just be very simple log n, because we'd always drop the constant. So we can say our time complexity is just log n. And look back at the next slide. It is true. Sweet. And so Now let's look at the case where it's not going to be logged in at all. So looking back at our two things again, the first thing it was our time was our input size, and we can see it is n, which is shown right here. We have our basically condition and return statement, which is just an O of 1. So we're not going to worry about that too much, but just for a little note. However, a return function does have two recursive calls, and we're also dividing our input size by half. So for second part, we're going to say, hey, how long are we using n for? So just looking at the actual input size, we're doing it by half. So knowing already, if we do n divided by 2, we should get a time complexity of log base 2 of n. However, to recall our big O tree, sometimes recursion will also be n to the power of x, which is a very bad time complexity, but that's okay. That's the power of recursion. So we're calling this function twice, once here, another times here. And so for this case, oh, there's two recursive calls. We're going to have a very horrible time complexity, and that's completely okay. Because for this time complexity, we can state we're going to have O of 2 to represent the two recursive calls to the power of log n, where we drop the constant, which is 2 in this case, and that's our final time complexity, which is true. If we look to the next slide, yay, it is right. Sweet. So hopefully you guys understand recursion time complexity from here, because from here on out, time complexity is going to be your best friend, especially for solving those very long, complex problems. So hopefully everyone's okay from here. And let's move on to array list this time. So you have seen this array list already from design books in your previous lab, and should be hopefully not too complex compared to a linked list, but that's okay. We're going to keep it simple. So an array list is just a dynamic array, nothing else. Can't really say it any more clear. But a few things to note for this exam is that I highly recommend that you know their time complexities, including what they do, like their basic pseudocode function. So for example, if I give you a question saying, hey, what's the time complexity if I want to insert an element to an array list? And let's say, for example, I want to insert it at this node. Okay, so we're gonna have to traverse this list, obviously. And since we're traversing and we don't know where it's at, but we do know we have a size of n, we can state, oh, since we're going from like 0 all the way until we reach n, since we don't know where we're going to insert it at, oh, that's simple. We've seen this before. We know if we go from 0 to n, step by step, we're going to have a time complexity of O of n, which is true. So when you're trying to insert to the array list, we should have a time complexity of O of n. And yeah, that's pretty much for array list, because I'm not too worried about this topic at all, but I do recommend you trying out to find these time complexities for finding, evaluating an array list, deleting, printing, and checking if an array is empty or not. Highly recommend it. And so now let's move on to the meat of this review, the linked list. So again, I recommend knowing how to implement a linked list class, their basic functions, and knowing what each function's time complexity is. Like when you're trying to add, delete, insert, print, checking if it's empty or not. Highly recommend. And so let's hold our horses and say, hey, what the hell is a linked list? That's okay. So a linked list, depending on how you structure it and define these classes, will consist of three things. The main thing we need to worry about is making sure we include a head, where the head will determine the start of the actual list itself. And it will also include a next pointer that points to the next node or null, depending on how you create your linked list. And so in between both the start and end of the list, we're going to have multiple nodes, which is the most inner part of the list. And at the very end, the end of the list also has a name, which is also called tail. You may see this in your double link list lab. And since we haven't talked about much tail in general, we can just refer tail as the end of the list. And for this, we have multiple links to a single link list, double, and circular, and these replets here. And we also have a simple structure we're going to follow for every single example from here on out, where we have a simple struct node, and this structure node has two very simple things, which includes the value of the actual node. So it can be, let's say our head will have the value 0, this will be 2, and our tail will be 5. And we also have the next pointer, which can be seen in our little drawing right here. We can see our next pointers are right here and right here. Hopefully simple enough to understand what a linked list is supposed to be. Okay, sweet. Now let's move on to the first example here. So this example is just a basic adding a element to the list. So we're gonna check few things. You have to check the first case right here. This is checking, okay, what if my list is empty? And if it is empty, we're basically going to start it from scratch. We can say, okay, we're going to make a new node, which will hold the value equal to a head and return, because it's an empty list. It's completely new. So we only have to declare the head and return out of this function. That's it. But what if it's not empty? So let's check the next thing. Let's traverse, which is this while loop right here. Traverse. There we go. Hopefully I spelled it correctly. We're going to basically traverse the whole entire list until we reach the last node, which our condition, which is seen at this while loop, will execute, basically stating, hey, what if I have a node, let's say, for example, the head node, the middle node, and this is the last node. And our condition is saying, hey, we're going to check the next pointer, and if the next pointer is not null, we're going to keep going. So let's say we start in here, and we're saying, oh, our next is not empty. It has a neighbor. So let's go to the next node here. Oh, it also has a neighbor. It's not the last node at all. Let's keep going. Oh, but this node does not have a neighbor, which should be null pointer, does not exist. So our while loop will stop here and say, okay, we're done. We have reached the last node. Let's now append a node to this part. So down here in this statement, when we do current next is equal to node value to a new node, we're basically just saying, hey, at the last index, we're gonna say our next pointer will be the new node. And yay, we inserted a new node. Compared to 3, we have now increased our size by 4. And so, pop quiz, what's the time complexity for this? So, as I drew this out, we can tell that I went from the beginning to the middle to the end, and then I added a new list. And so, this seems kind of familiar. It should be. We're basically saying, hey, we're going from 0, the beginning, all the way to the middle, all the way to reach the end, which let's say our size is n. Oh, but wait, we have seen this before. We can immediately tell, hey, this is the time complexity of O of n, because we're going to traverse the whole entire list until we reach the end. And yes, that's how our time complexity should be. That's correct. Yay. So now, getting this general really simple code. Let's move on to the next thing. Okay, let's insert into a list this time. So again, what if our list is empty right here? So empty list. And I was just saying, hey, we're gonna set a new head and exit out. We created a new list entirely. Yay. But what if I want to insert at the actual head itself? Oh, well, that's a interesting condition you have to worry about. There's like so many things you have to worry about for a linked list. So what if the head is target? So, and we're going to assume that a list is not empty in this case. So if we trace this out, we have a node and another node right here. And I'm basically saying, hey, if I index as 0 and my head exists, we're gonna assign a new node as the actual head, which is gonna be in the red, but we're gonna take two parameters. We're gonna take the value itself and current, where current is our old head. So in other words, this is current and this is our new head. And we can say, oh, easily, we can say head arrow next will point to C, which is current node. Yay, because this was usually our old head, but now we're going to insert a net node previously. And that's it. And for the other aspect of this insert, we're going to traverse again all of this trunk right here, traverse. But while we're traversing, we're going to check, hey, is our counter the same as our index we're looking for? Oh, if it is, cool. Then yes, this is the actual index I'm looking for. Okay, sweet, yay. Excuse me. We can state, okay, we're gonna create a temporary node as our new node where we're gonna send in the value, but we're gonna point current to the next variable. So we're just saying, let's say we have one node, middle node, and an old node. Let's say our current is index 1, which is right here. We're basically saying, hey, let's create a new temporary variable. Let's just say it could be down here, call it T for temp. And we're going to have current arrow next be our next pointer for this list. So we're going to point to the next pointer. And we're going to set our current pointer, which is right there, as our temp. So we're going to move this arrow and we're going to point to our temporary variable instead. And whenever we reorganize this again, we have one node, two node, red node, and green node right here and right here. That's all we did. We inserted a node between our list, which is sweet, which is exactly what we're trying to do. And worst case scenario, we never find the index. We're just basically going to add to the end as we did with the add. The exact same call, exact same everything. So looking at this again, we keep traversing the entire list from the beginning to the end to the middle, all over the place. So we can tell we're going from the beginning all the way from the middle, and we're going to stop here. Maybe we're going to stop at the end as like the last test case. So we're going from 0 to n again. Huh, strange. Isn't it O of n again? Very weird, right? We keep seeing O of n popped up everywhere. Well, that's on purpose. Linked lists are super optimized, but they're horribly too difficult. Very difficult to code. And that's how it should be. Because linked lists are the most optimized, well, average optimized data structures we'll ever actually see. And technically they're one of the hardest as well. So why are we learning linked lists? Because they're really important. They're like the foundation of data structures itself. And it allows us to have more freedom whenever we do matrix multiplication, which is like a lot more harder. But like I said earlier, this is the hardest topic. So if I can do a linked list, I can do anything in data structures. It's like math. Whenever you first started doing plus, adding, subtraction, whatever, but now you're doing like calculus 1, calc 2, maybe calc 3 if you're trying to be bold. Exact same thing with a linked list. You have to start at the basics, go over that heap, and you're gonna be okay from here. And so going back to the linked list problem, we know it's O of n, sweet. Now let's look at this delete function. So we can tell we have a condition here saying, hey, my list is empty. If it's empty, do nothing. So we can say list is empty. And then we have a condition here saying it's not empty. Let's just delete the head. So let's say, for example, we only have the head pointer itself. And so we're going to save this head into a temporary variable, which could be seen down here. We're going to iterate to the next pointer, but in our case, there is no next pointer, so it'll just be null. And now we just delete temp from existence. There. And we just basically reset our list back to an empty list itself. Okay, but will this work with other nodes? It should. So looking at the previous example, let me just go this up a little bit. Let's say, for example, our node is not empty. We have a neighbor instead. So we do the same thing again. So let's read this real quick. So temp is gonna be the red one. We're gonna go to the next node. Okay. So we're gonna make this our new head. And okay, sweet. And now we're gonna do this delete temp again, but since temp is equal to the previous head, we can just state, oh, this temporary variable will never exist again, including the actual pointer itself. So whenever we run the delete temp, we're basically deleting the temp and the current node we're basically pointing towards. So these two nodes. So they're basically going to be gone from existence. And we'll either have a null list, which is empty, or we will just iterate to the next pointer inside head. And so, knowing this, what's time complexity? Since we're not really iterating through a list, and we know head will always be at the beginning, I don't know. I It can't be O of m because we're not iterating. So, and it can't be log m because we're not doing anything by half. So, interestingly enough, this time complexity is going to be O of 1. Because just remember, few key things. The head is always going to be the first thing you see in your list. So head is first. And so since the head is like the first thing you will see every single time, we don't need a traverse. We're not going to do it by half either. It's the first thing we see. So it will happen instantaneously. So it will have a time complexity of O of 1. Wow, that's pretty cool. We got kind of lazy and bored of seeing O of n a lot, so let's just mix it up a little bit. Can't say it for the next ones, but that's okay. So O of 1, sweet. What happens if we do delete add cell? Okay, so let's look at this again. So this is saying it's empty. Yeah, whatever. If it's empty, we can't really do anything at all because we're basically done. So let's check the next one. What is this saying? Oh, so this is just checking, hey, what if my head is the only node that exists? So we're just saying head pointing to null. Since head, let's say, is the only node, we don't have to worry about making another temporary variable or like worrying about the next pointer itself. We can just delete the head automatically, but we do need to do one little thing. Since our other function just said head arrow head will equal head arrow next, where we could just assume head arrow next is no pointer, and we're not going to use a temporary variable here. We just say, oh, since we're deleting head, we're basically deleting it from, we're wiping it from our computer. And if we want to use it again, we don't know where it's at. And so let's just state that we don't know where it's at. We just lost it. We're going to cause a core 11, core negative 11, core 6 even. Horrible, horrible, horrible bug. But one simple thing will save you. Just initialize head back to null. So our head will equal null again. This is because since no pointers is in other words just saying a 0, since actually let me rephrase that real quick. Since computers only know ones and zeros, and if we're using a head, the computer will automatically read it as like, oh, it's 1 since we're using this. But if we delete it, we'll be like, wait, is it 1 or 0? Wait, what's going on here? So just resend it back to no pointer to just tell the machine like, hey, this list is empty. Let's just power off this list because it doesn't exist anymore. So just turn it back off. Turn it back to 0. And that's it. That's the whole entire thing of this condition. It's just saying the head, it's, by itself. We don't know if the next pointer is null. We can just delete the head, set it back to 0 so the computer knows it does not exist anymore, and just return. And that's it. And so going to the next parts, we have current and previous, where current will be the head, previous will be a null pointer, since we're going to do a little fast and slow pointer type of paradigm here. And we're going to basically traverse this whole entire list again. So traverse. And we're gonna keep it track that our previous will be current, current will equal next pointer. So just draw this out real quick. So initially we have as current is head, and our previous does not exist yet. And so when we go to the next part, we can see current arrow next. We can see that we have let's do previous here now as our current. Well, previous will hold the current position of current. That's a tongue twister. And then current will go to the next pointer. So we'll go here instead. Okay, so we have previous and current. And then again, previous will go to the current position of current. And then current will go to the next one afterwards. Here. So it's just a little game they're playing. Like, hey, save this for me while I go to the next one. Hey, save this off for me again and I'll go to the next one. That's it. Because since we want to delete the end of the list or the tail, we want to delete the last node, which is this node right here. And so whenever we reach the end, as we say, current next will be null pointer, which is true. Our current next is null. So we just delete x, and then we just assign the previous pointer as null. So in other words, will point to nothing. Because remember, again, we can't just delete it and just leave it alone. We have to make sure the machine knows that it is zero, it is off, it does not exist. So since we're traversing again, and we're going to go from either 0 to 1, or we go from 0 all the way to reach the end, which is the tail. Easy again. It's O of n every single time. O of n, because we're traversing the whole entire input size. So yes, O of n, yay. One more, the last linked list. So this one is stating, hey, let's delete a value this time. Instead of deleting the head or tail, let's just delete the value. So this is empty again. If it's empty, do nothing. And so this one's saying, okay, what if my head is the value I'm looking for? Okay. So we're saying, okay, let's create a basic linked list like as so. And we're going to make a temporary variable. Let's make this a red color instead to make it a little more easier to read. And this is my old head, but now I'm going to go to the next pointer over here. So this will be my new head. Let's just erase this. Now this is my new head. And since this is a temporary variable, I don't have to worry about resetting head back to null at all, since head has already been moved to the next one. We can just say, okay, delete this. The exact same version, the exact same thing we did when we did delete head. The exact same thing. So we're done. We're just deleting that head. That's it. And so again, we have current and previous from the previous example again. And so let's read this function while loop real quick. And we're traversing again from like here to there, from the beginning to the end. However, we're going to keep track of one simple if statement. We're saying, hey, what if the current value is the value I'm looking for? Ah, okay. So let's draw this one out because it does get a little more complex. So let's say we have a node and we're looking for the middle node. This is our target right here. And so let's run this loop. Let's run through this whole entire array again. So we're looking for you, the one in red. So let's say, okay, this is our current value. No, this is my previous value. And this is current. As we said before, head will be previous and current will be head arrow next. Because we know if it's the head, we already take care of that at all. So we don't have to worry about any other cases at all. So let's read this real quick. Oh, excuse me. Okay. So we're saying, hey, is my current the value I'm looking for? The answer is yes. Yes, it is. So we can state, okay, our previous arrow next will now be current arrow next. So we're making a huge jump to the next node, and we just delete current this time. Because remember, we basically did this. My bad. We're stating that current as my target, as the one I'm looking for. And so instead of having an arrow from here, we're gonna have an arrow all the way over here instead. So this arrow go completely gone, kazammed. And so now we're just gonna delete current because we know this will just not exist anymore, and this pointer should not exist because it exists inside the structure itself. And that's it. We're just saying that. And that's pretty much it. We just deleted a node that was in between two different nodes. So again, we're traversing. We have, if the head is the value itself, that's like the O of 1, basically our same time complexity of deleting at head. But here, we're always doing traversing through the list itself again. So if we go from 0 all the way to n, so this little while loop right here will take O of n. And since this O1 constant is just 1 itself, we can just state, hey, my time complexity will be O of n again. Wow, really strange. But congratulations, you've done it. You've reached all the way to the end of a linked list. And see, we have O of n. Sweet. And also, I didn't make a notice at all previously, but in every single function, you can see a little note saying like what is the actual function doing. So this is a deleting the value ahead. As we said before, we're checking if the head is empty, or if the head is the value to delete, or we just iterate through the whole entire list itself. So it's a little bit bonus for y'all to read through it in case you didn't understand or got lost at any point. But that's there for y'all for your benefit, and yeah, please use it if you ever get stuck. And so, again, I will get angry. We need to worry about a few things. Other functions, like let's say I want to insert to a double or circular. I want to insert to the head or tail this time, or deleting from multiple different iterations of a list, or printing it again. So don't stress. Remember, you can trace each function as a part of the Discord that you as part of the resources Sneha dropped, and you can just draw them like saying like, hey, let's for example take printing. If I want to print the whole entire list, so let's say I want to print these 3 nodes. So obviously we have to start at the beginning and we have to reach the end. So printing a linked list, no matter what, it's always gonna be O of n because we're always gonna iterate through that whole entire input size every single time. So just draw it out. And if you want even more help, more work, even though it sounds really scary, whoa, look through your labs and look through your functions you created. Can you tell me the time complexity of those? And once you feel confident enough, you will be okay and you will be fully prepared for this exam. Okay, so I may have lied. And we have a bonus topic. Whoa. Well, no one saw that coming, not even me. That's crazy, even though I was the one who made the slides. That's insane. So let's talk about matrices. Very important topic to know, especially for the lab you have currently. So let's talk about what the hell is a matrices? Like, I never heard of this. I never took linear algebra or just skipped it entirely. Well, not to worry, not to worry. So a matrix is just a 2D array. That's it. So you can have multiple variables. Let's say a matrices filled of all twos, or matrices that you can fill all on your own. That's all we're gonna worry about. And we're not gonna worry about too much like what if I'm doing the math correctly or what if I'm doing this wrong. Don't worry. We're gonna take care of that right now. And so since we're gonna speed run through this topic, let's worry about 2 things. It's a 2D array. So you're gonna need 2 for loops every single time you work with a matrices, because you're gonna have to iterate through the row and columns. So you're gonna assume that I will be the rows, and you have a separate variable called j, which will run through the columns itself. So you're gonna need 2 for loops every single time. A little hint, by the way. So let's look at this. Let's do addition. So we're just doing a simple addition here. And this is like an example of how addition works here, but you don't have to worry about how it works. Just remember how it looks through code. But you do know one thing. We are creating a new matrices every single time we do addition, subtraction, multiplication. As we see the theory down here, if we do A plus B, we'll get a new array equal to C. Whoa, that's pretty crazy, right? And so looking at this basic function here, we know we're going to iterate from 0 to n, where I is going to be our rows, and j is going to be from 0 to m, where m is going to be the column itself. Even though it looks really confusing, not to worry. You just need to know what is going on. And from here, you can see we're doing C, a new matrices for I and j, and we keep doing A plus B at that certain row and index. Row and column, my mistake. And that's it. And so based on this function, time complexity will obviously be O times n by m, because we have a nested for loop, which will go from 0 all the way until n, and we have another loop that will go from 0 all the way until m. And as the previous ones we have seen earlier, we can tell this will be O times m for additional loop, because we have two for loops right here. And that's pretty much it. You just have to know how it looks like, what's the complexity. It's nice to know, and just know that it'll be okay. And so now let's look at the next one, subtraction. So doing addition, the only difference really is just the minus sign. So again, to iterate one more time, we're doing A minus B, and we're going to create a new array called C. And here we can see, yes, we're doing a new array C, A minus B every single time. And again, we have two nested for loops again. So we have I going from 0 all the way until n, and we have m going from 0 all the way until m as well. And so again, it's a nested for loop. You've seen this already before. You can just say, oh, it's going to be O n times m again. Crazy, right? It's almost like they're the exact same thing except one small difference. Insane. But what about multiplication is tied? A little bit more different. A little different, not gonna lie. So again, our theory is the exact same thing. Here's an example down here if you want to take a look at it. And now you know A times B will equal a new array called C. So we're gonna need something completely different here. As you can tell, a triangle complexity is not n times m anymore. It's different now. Only because we have to keep track of a certain rule in multiplication where you have to check certain rows and certain columns based on their positions inside the new matrices here. So, and that's kind of a bummer, because if you have to do multiple checks for like checking like what if I'm at this certain this position, or next position, seems odd. Seems like another for loop, you might say. And so this is our code. We can just say that we can initialize back to zeros to make sure like all the values are consistently 0. And when we do multiple multiplication, just keep adding the resulting multiplication you get to the table. And since we're starting at 0, we just do a plus equal sign to initialize it to that. So we don't have to worry about that though. We only have to worry about with our eyes, what is the time complexity for this? So we can tell the first loop will go from 0 to n again, but our second loop will not go from m. So we'll go from p. Well, p will represent the position at the position of the matrices that we're trying to do the multiplication for. So let's say for 29, that's to worry about column 1 of B. That's to worry about row 1 of A. Ah, oh, so confusing. Don't worry about it. Just remember, no, you have an extra iteration up. And for the last one, we know we're going from 0 until m. Pretty noticeable, right? Since these are nested for loops, we have to use multiplication again, which sucks, but that's okay, because you just have to add up all the variables together now. So you have a time complexity of n times p times m. Or if, as a small chance that all the sizes are the same, you can also say this n cubic. But for now, since they're all different variables, let's just say they're all n times m times p. That's it. And a little fun fact is that you can also make matrix multiplication very efficient whenever you implement exponential by squaring. But I'm gonna let you guys research that certain topic, because that topic is interesting to my dear heart, because it does involve a little bit divide and conquer principles, which you'll learn either in this class or in your previous class if you forget about it, or your next class if you forget about it. Not to worry. But That's for your own research sake, and that's all I'm gonna say for this topic because that's it. You made it to the end. Yay. And so a quick summary is that we covered Big O. Sweet. Wrong thing I'm trying to highlight. Time complexity. Okay, nice. Recursion, list, and matrices as a bonus. Look at that. And so only a few notes I can say is that so definitely take advantage of your cheat sheet. So like I recommend using theoretical questions, knowing time complexities, knowing what this algorithm is doing, why we're doing this, and like having like a basic understanding of like every single topic here as well. Like know what you're trying to get, know what you're signing up into. Really important. Just take advantage of it. And also for like the coding aspect of it, you're gonna have Zybooks there, so you can just use Zybooks for coding problems. So I highly recommend just use your cheat sheet for the first part, and then the next part just use iBooks because you have an open resource to that. And the next small thing is that don't stress too much. It's gonna be okay, even though someone else, another T I'm not gonna mention, cough cough, added a separate message. It's gonna be okay, even though it doesn't feel like it. Just know it is going to be okay. So hopefully that was a little bit useful for at least one person today, and I hope you have a wonderful time taking the exam. And also, if I can type or write this out, thank you for watching.